Okay, good morning, everybody. Let's get started. So I think we did finish the synthesis of a lipid, right? Focusing on the lipogenesis and triglyceride. If you guys still remember, the two different process, right? Fatty acid synthesis or lipogenesis versus triglyceride synthesis. So let me just ask you, so what is the starting molecules for lipogenesis or fatty acid synthesis? Do you remember? Which one is starting molecules or building blockers molecules of fatty acid synthesis? Acetyl-CoA, I heard somebody say, right? So acetyl-CoA, right, is a 2 carbons and molecules and synthesize, the fatty acids. So where does the acetyl-CoA come from? Lipolysis, right, from glucose and amino acids, right? The oxidation to the pyruvate and to acetyl-CoA. Okay. And what about the triglyceride synthesis? What are the substrates of triglyceride synthesis pathway? Substrates too, right? Fatty acids and glycerol backbone, right? Very good. Okay, so and which tissues does the most lipolysis? Lipogenesis. Which tissue does most lipogenesis? Liver. Yeah, liver is the main tissue that does lipogenesis, fatty acid synthesis, right? And which tissues we usually store lipids or triglyceride or fatty acids? Adipose tissue, right? So, and we also talk about this slide. Fatty acids is synthesized in the liver, right, through the lipogenesis pathway, right, converted actually glucose or amino acids to fat, right? But finally, the fatty acids need to be stored in the adipose tissue in the form of triglyceride, right? You still remember? And also, fatty acids, once it's synthesized in the liver, needs to be first synthesized or converted to the triglyceride in order to be transported, right, from the liver to adipose tissue. And another thing that I also mentioned, that triglyceride cannot be simply transported, right? Cannot be simply transported to the fat tissue without any help. So the lipoprotein is a group of protein that actually help the transport of triglyceride, right, from liver to adipose tissue or from small intestine to the adipose tissue. So we talk about we mentioned the one very important enzyme called lipoprotein lipase, LPL, right? LPL is very important. What LPS does is to hydrolyze or break down triglyceride in the VLDL or in the chylomicron to release fatty acids and glycerol. And fatty acids now is are able to be uptaken by adipose tissue. Triglyceride molecule is too large, right? Cannot be directly uptaken by fat tissue, so need to be break down again into the fatty acids and triglyceride, and free fatty acids now is able to be taken into the fat tissue, fat cell. And once inside of fat cell, fatty acids again need to be re-acidified or called resynthesized, right? You triglyceride and then stored in the fat tissue or fat cell. So now we're going to talk about the lipoprotein lipase, LPL. Again, this is a very important enzyme. What LPS does is to hydrolyze or break down triglyceride in lipoproteins, right, in both VLDL or chylomicron, and to release fatty acids. And this process basically occurs in the circulation, but usually inside of a fat tissue, but not in any type of cells, but in the blood and in like capillary, right? You know, it's very close to the cells. So once it's fatty acids released from triglyceride, then can be immediately taken up into the cells. So lipoprotein lipase, LPL, can be synthesized by two tissues, the adipose tissue and muscle. And the thing is, we're not talking about the muscle yet, but just want to mention the LPS synthesis and secretion from adipose tissue or from muscle. The regulation of the LPL synthesis and secretion are different between liver and muscle in terms of, you know, the physiological condition or the role of the LPL hydrolysis, right? So now here we just talk about lipoprotein lipase that's secreted from adipose tissue. And basically, it's LPS is localized on the luminal face of the endothelium cells of capillary, right? So it's in the circulation, but it's very close because it's secreted by fat cell, right? So fat cell secrete it immediately into the capillary, right? So so they basically only hydrolyze triglyceride when it's rich or when it's arrived in the adipose tissue, right? Does that make sense? Okay. So and catalyzes hydrolysis of triglyceride to fatty acids and glycerol. So this is a function of LPL. And regulation of LPL synthesis and secretion is different again in adipose tissue and muscle, but in adipose tissue here, LPL is synthesized or secretion is increased in the fat condition, right? And muscle LPS is increased during the fasting or exercise, right? So again, the regulation of LPS in adipose tissue and muscle is different. The adipose tissue LPS synthesized secretion is increased during fat condition, which makes sense, right? During the fat condition, we have increased lipogenesis, and we have increased transportation of triglyceride from liver to the adipose tissue, and we need to break down triglyceride and take up fatty acids for storage. So fat condition, adipose tissue LPS is increased, right? But muscle LPS, it does a little bit different role. That different role. During the fasting, when muscle need fatty acids for energy, right? So, but fatty acids usually, again, is also packed into, form as the triglyceride and packed into the lipoprotein being transported to the muscle during fasting condition. So, under the fast condition, muscle LPS increase and hydrolyze also triglyceride, right, and pick up fatty acids. But these fatty acids will be oxidized during the fasting condition for energy in the muscle, right? So in the adipose tissue, I'm not trying not to be confused, right? So in adipose tissue, LPS again increase in the fat condition, right, and take up fatty acids, and this fatty acids actually re-acidified to triglycerides stored in the adipose tissue, not utilized, right, in adipose tissue. So the regulation, under the different physiological condition, and also the fate of the fatty acids once it's get into the fat cell or get into the muscle, and also different, right? I think we all cover all this, right? So in fat tissue, fatty acids formed from, released from triglyceride by LPS and re-acidify. Yeah.
You just said LPS.
Oh, I'm sorry. LPS.
I was just like kind of getting confused. I want to make sure I have
I'm sorry. Because why I said LPS, he's laughing. So, because we study a lot, LPS is actually liposaccharide. It's kind of a component from the bacterial wall. So it's very inflammatory, at very high inflammatory activity. So we did doing kind of experiment research using a lot of LPS. So that's why my mind always kind of apologize. LPL, all right? LPL, lipoprotein lipase. Okay, so summary of the triglyceride synthesis, and I think I'm not going to go through all this, but you guys, try to remember, understand how the process, right? The triglyceride synthesis and fatty acid synthesis, and how they are regulated. Okay. All right. So now let's talk about oxidation of fatty acids and ketogenesis. So what do you expect? In which physiological condition you will expect the fatty acid oxidation or ketogenesis will increase or activated? In which physiological? Fat or fasting? Fasting, right? So before we talk about fatty acid oxidation, I wanted to mention that mobilization of triglyceride. So we know fatty acids usually are stored in the form of triglyceride in adipose tissue, right? During the fat condition, when we have extra energy, right? We can't use all energy that we obtained from the diet, so we store in the adipose tissue. And what about this is the lipid storage, right? What about the carbohydrate storage? Which forms of the glycogen, right? So carbohydrate, we store the carbohydrate in form of the glycogen, right, in both liver and muscle, and we store the lipids or fatty acids in the form of triglyceride in the adipose tissue. So just want you guys to remember this, right? Still. And this slide tells us the process of the storage triglyceride, right? Of course, under the fat condition. And lots of, I think, a pretty busy slide. So, in addition to the fat, or fatty acids that we uptake from the diet, that definitely we stored as a triglyceride in the fat tissue, right? What other nutrients that we also can be, other nutrients can be stored in the form of fat or triglyceride? Yeah, glucose, right? We just talked, right? Glucose and carbohydrate, right? And also some of the protein if we have really high protein diet. So, so let's see, under the fat condition, when we eat a meal, then we have dietary fatty acids, right? We can digest, absorb into the body. And if you still remember the chylomicron that is synthesized in the small intestine or enterocytes can pack the triglyceride, which initially absorbed from the diet, right? And transported the triglyceride, dietary triglyceride, right? And from small intestine to fat tissue for storage. And again, we just mentioned lipoprotein lipase, LPL, as the enzyme that first break down triglyceride and release fatty acids, and then fatty acids enter the fat cell for storage. But again, we know that fatty acids has to be resynthesized triglyceride, right? Re-esterified, we call it also similar term. Concept. So we need a glycerol 3 backbone, right? Glycerol 3 phosphate. And we also so some of the triglyceride from the small intestine can be transported to the liver. Although the majority of the triglyceride being transported to fat tissue directly, right, for storage, but it would still have some, small amount of triglyceride being transported to the liver, and be, break down fatty acids and resynthesize triglyceride, and packed into the VLDL, the different lipoproteins, right? And similarly, VLDL, the triglyceride in the VLDL need to be break down by LPL and to fatty acids, and fatty acids also uptake by fat cell, right? Okay, so. And we also get the carbohydrate, right? We get the glucose from the diet. So glucose, if you still remember, that uptake by fat cells and contribute very important substrate for triglyceride synthesis, which is the glycerol 3 backbone, right? Glycerol 3 phosphate through the glycolysis pathway, right, during the fat condition. And of course, some of the glucose can go to the complete oxidation pathway, right, enter the mitochondria and TC cycles and for complete oxidize. And some of the citrate that from the TC cycles can be transported out of mitochondria to cytosol for lipogenesis, right? If you still remember, and also contributed to some of the fatty acids. But I wanted to remind you that the majority of fatty acids in the adipose tissue, in the fat condition, actually coming from the circulation, which is diet and also from lipogenesis, right? Only very small amount of fatty acids can be synthesized in the fat cells through the lipogenesis pathway, right? So, dietary carbohydrate glucose can also be uptake, and actually majority of the glucose is metabolized in the liver, right? Through the glucose metabolic pathway, glycogen synthesis pathway, right? To synthesize glycogen in the liver, but the extra glucose can be converted to fat if we particularly eat the high carbohydrate diet, right? Carb can be converted to fat through the lipogenic pathway in the liver, and then back to the VLDL in the form of the triglyceride, and then also can be transported to the fat cell for the storage, right? Is that clear? Any question about this whole process? The storage of triglyceride, and you need to know where the fatty acids comes from and the glycerol backbone comes from, right? And in this, the whole storage process. Okay, now mobilization of triglyceride. So during the fasting, we do not have enough glucose, right, from the diet. So we sort of under the energy crisis, right? And two important tissue and organs that requires glucose for energy. Do you still remember? Which are these tissues? Brain and red blood cell, right? So we have a limited glucose during the fasting. So these two organs are the priorities, right? Organs that we need to give the glucose to these two important organs because they are heavily rely on glucose for oxidation. So what we need to do, our body need to do to generate a alternative fuels, right? So fatty acids are the very, very important energy fuels during fasting. So we break down the triglyceride in the fat tissue and release fatty acids into circulation. So raise the fatty acid level and to provide fatty acids and for other tissue used as energy, as alternative energy, right? So in this way that we can save glucose and for primarily for brain and red blood cell use energy. So under the fasting condition, the liver does important thing, for example, to do the gluconeogenesis and to break down glycogen, right, to release glucose, and all these activities and reduce the glycogen synthesis pathway. So all these activities of glucometabolism, the purpose of this is to maintain blood glucose level to allow the more glucose being used by brain and red blood cells, right? And in the meantime, the fatty acids being released from fat tissue and be used by primarily muscle. So muscle is a main tissues that utilize fatty acids as energy fuel during fasting condition. And liver also takes a lot of fatty acids And just keep in mind that the function of liver is different from the muscle. So liver will also oxidize fatty acids, but not completely oxidize to produce ATP. Rather, actually, liver is a very, very important tissue that does the ketogenesis. So liver can utilize a lot of fatty acids, but the purpose of this utilization is not to oxidize for ATP production, but is to synthesize ketone bodies, right? So ketone bodies are synthesized by the liver and released into circulation. So ketone bodies is another alternative energy fuel during fasting condition, in addition to fatty acids, right? And ketone bodies, the two main tissues that utilize ketone bodies are brain and fatty acids. The muscle, right? So muscle, once fatty acids uptake into the muscle, that muscle be able to completely oxidize fatty acids for ATP production, right? So you wanted to know the difference, in terms of fatty acids metabolism between liver and muscle, right? That's a different thing. And I also want to mention, if you probably don't see any arrow from fatty acids to brain, right? So brain actually cannot use the fatty acids because of the molecules. Fatty acids are too bigger, right? So brain cannot, fatty acid cannot pass those called the brain-blood barrier, right, to get into the brain. So brain is only be able to use the ketone bodies as the energy fuel during the fasting. But primarily energy fuel for brain is still glucose during fasting, but only when very long-term starvation, right, and brain start to utilize ketone bodies for energy. Any question? So this is also the reason why our body need to synthesize ketone bodies, right? Because brain cannot utilize fatty acids, so we need to synthesize the much smaller molecules of ketone bodies, right? So allow brain to be able to use for energy. So what do you think the energy fuels the body can use actually different, right, between fat condition and fasting condition? What are the energy fuels that our body can use during fat condition? Glucose, right? Yeah. So energy fuel that our body use primarily, glucose under the fat condition. And what about the fasting condition? Energy fuels? Yeah, fatty acid, ketone bodies, and also glucose, right? So, and depend on the tissue, right? Okay, so now let's get a little bit detailed how triglycerides mobilize or break down fatty acids and release fatty acids. It's just the details, right? The involve the process of triglyceride breakdown or hydrolysis, and also the enzymes, hormones that involve this hydrolysis process. So you probably all know, right? Under the fasting conditions, we expect the glucagon and epinephrine level will be increased. But how about the insulin levels? decrease, right? So we have a decreased insulin levels and increased epinephrine and glucagon level. So cyclo-AMP, CAMP, I mentioned earlier, right? You also expect increase in response to high levels of epinephrine or glucagon. And cyclo-AMP, let me just talk about this, the whole process first. So triglyceride can be broken down to 3 fatty acids and glycerol backbone. And this process, we have several different terms to call this. Like sometimes we call it lipolysis, right? And sometimes called the hydrolysis of triglyceride. So basically, it's the same thing, right? We talk about this process. And this hydrolysis or lipolysis of triglyceride catalyzed by several enzymes. I listed here, the HSL, the hormone-sensitive lipase. ATGL is adipose tissue or adipose triglyceride lipase, and MTGL is the monoglyceride lipase. So the 3 different type of lipase, they hydrolyze the different substrates, right? But the overall function, they are actually the same function, is try to break down the triglyceride and release the free fatty acids, right? And HSL, I put only HSL here because HSL, or like hormone-sensitive lipase, is a very old enzyme that has been studied for a long time. So we know very well about this enzyme, how this enzyme is regulated, right? So that doesn't mean that the other 2 enzymes do anything, right? But again, just because we know very well about the regulation. So by the enzymes, by the hormones. So again, let's go back here. So during the fasting, we have increased epinephrine, glucagon, and causing increased CMP levels, which stimulates protein kinase A activities, right? So raise the protein kinase A. So protein kinase A is an enzyme that can catalyze the phosphorylation of HSL, so causing the phosphorylation of HSL. So once HSL gets phosphorylated, its activities increase, so causing the active, right? So this is an enzyme that can hydrolyze triglyceride and release fatty acids. And what insulin does, so under the fat condition, right? So basically, insulin does the opposite function in terms of phosphorylation. So insulin basically dephosphorylated HSL, causing inactive, right? But because of the fasting condition, we have a lower insulin level, right? So the effect of insulin on the dephosphorylation or inactivate HSL, this function is also decreased, right? So that means we have a more HSL is phosphorylated and more HSL are active. Does that make sense? Right? So counterbalance, the 2 counter-regulatory hormones, right? So eventually, we have lots of fatty acids that been released from fat cells during fasting, and the liver picks up lots of fatty acids. Again, it's not for complete oxidation, ATP production, but for synthesis of ketone bodies, right? But of course, fatty acids, pick up by muscle and other tissue for use as alternative energy fuels. And glycerol is also released, right? glycerol, if you still remember, is the one of the precursors, right? The gluconeogenesis. And under fasting condition, we also have gluconeogenesis activities being upregulated, right? So the meantime, glycerol is released and picked up by liver for gluconeogenesis. So again, during the fasting, liver does the two most important things. One is uptake fatty acids for ketone body synthesis, and also pick up the glycerol for gluconeogenesis, right? So liver is works very hard, right, during the fasting to maintain blood glucose level and also to increase the alternate fused ketone bodies. Okay, so hydrolysis. For hydrolysis, again, this is the full completed process, right? The lipolysis or hydrolysis. So triglyceride, if you still remember, has 3 fatty acids attached to the glycerol backbone. We give the position, right, SN1, 2, 3, right, to name the different carbons. And ATGL, adipose triglyceride lipase, and this enzyme actually does this function first. So the triglyceride is the substrate of ATGL. So ATGL, when it does function, the one fatty acid is released, right? And then you still have 2 fatty acids attached to the glycerol backbone, and this molecule is called diacylglycerol, right? You have 2 fatty acids still attached to the glycerol backbone. And diacylglycerol is the substrate of HSL, right? So HSL then also cleaves one fatty acids from either from SN1 or SN3 position, and release another fatty acids, and then you have one more fatty acids left. This molecule is monoacylglycerol, right? So finally, monoacylglycerol lipase does the job and cleaves the last fatty acids from the glycerol backbone and release glycerol, right? So 3 enzymes work together to remove all 3 fatty acids from glycerol backbone, right? And you release the free fatty acids and glycerol molecules. And just get the details. So this is the reactions for glycerol for ATGL enzymes. So again, the triglyceride, 3 fatty acids, right, attached, and once the ATGL does its function, then you remove the one fatty acids, right, from either SN1 position or SN3 position. So you generated the diacylglycerol molecule, so the fatty acids attached either SN1, SN2, or SN2 and SN3 position, right? And then the second step is the HSL and cleaved fatty acids. And so after the hydrolysis of ATGL, we have 2 types of diacylglycerol, right? And depend on which position fatty acids attached to the glycerol backbone. So HSL hydrolyzed fatty acids from either SN3 or SN1 position, and eventually you generate the monoacylglycerol, and this molecule, you have one fatty acid molecule still attached to the SN2 position, right? So last, one more enzyme called ATGL ATG hydrolase, right? This enzyme is also can hydrolyze fatty triglyceride, but the activity compared to other three enzymes is relative low, right? It's not so active. So we usually don't talk too much about this. And the last enzyme MTGL does the function that cleaves the last fatty acids from SN2 position, right? Sorry, this is the, that's here. So cleave this fatty acids from SN2 position and release, glycerol, backbone, and finally 3 fatty acids, right? So fatty acids, once it's released from the triglyceride or glycerol backbone, they can just simply diffuse out of the fat cell, right, and into the circulation. And in the circulation, lipids, try to remember, lipids always bind to a protein. They never been free, circulating as a free molecules, right? So they are most of the fatty acids actually bind to the albumin, right? You guys know, right? Albumin at very high levels in the circulation. So most of fatty acids bind to albumin. For example, 2 to 3 fatty acids can bind 1 molecules of the albumin. And where does the circulating fatty acids go once it's released from fat tissue? What do you expect? Utilized by other tissues, right? And muscle is the most important tissue that uptake fatty acids for use as energy, I mentioned. And also liver picks the fatty acids, right, for ketone body synthesis. So during the fasting condition, about 2/3 of the fatty acids released from adipose tissue actually goes to muscle. Right? So like almost 70% of fatty acids that are released from fat tissue, they goes to muscle and utilized by muscle for energy, and 1/3 to liver for ketogenesis, right? So, of course, the other tissues can also utilize some of the fatty acids, but in very small amount. Right? The majority of the fatty acids utilized by muscle and and liver for ketogenesis. Okay. Do we need a break? Okay. All right. Okay, everybody, let's move on. Okay, so I have a kind of class activities, right? So can you guys talk to your neighbors and about to focus on these questions, particularly question 6 and 7, the highlight blue, right? About the hydrolysis or mobilization of triglyceride, right? Take a couple minutes and talk about it. All right. So, so how does it happen? And triglyceride mobilization. When do we need to mobilize triglyceride? Fasting condition, right? And what is where does it occur? In which tissues? Triglyceride mobilization. Which tissues? Can which tissues? Yes, adipose, right? Because we store triglyceride in adipose tissue, so mobilization also should occur in the adipose tissue, adipose cell. And which enzymes are involved? We talk about 3 enzymes, right? HSL, HSL, and ATGL, HSL, and MTGL, right? But you just wanted to focus on HSL, right? And where are the enzymes located? Yeah, maybe this is too broad a question. Like inside a cell or outside a cell? Inside a cell, right? Like lipase, HSL. And how do insulin, glucagon, or epinephrine, or if I didn't write here, regulate the activity of enzyme? Let's take HSL as an example. How insulin regulates HSL? Inactivates, right? Inactivate, dephosphorylate HSL, inactivate HSL. And what about epinephrine and glucagon? activated, right? It's increased HSL and phosphorylate HSL. Okay, now the question number 6. What are the major energy fuels during fasting? Yeah, fatty acids, ketone body, and glucose, right? But amino acids also, is a energy fuel, but we haven't talked about protein metabolism yet. And okay, so where do energy fuels used during fasting come from? Like, for example, fatty acids. Right. So basically, it's from adipose tissue, right? From the triglyceride breakdown. And what about the ketone bodies? Liver, yes, liver. Ketone bodies synthesized in liver. So liver is the main tissue that synthesizes ketone bodies. Okay. And what about glucose? During the fasting, circulating glucose, liver, right? Through the glycogen breakdown and gluconeogenesis, right? Okay, very good. So let's see. Oh, the question. Well, we just talked about it, right? So, and this diagram, I just wanted to emphasize again, during the starvation, triglycerides stored in the fat tissues being break down and release fatty acids, right? So I hope a diagram help you to remember, understand all this, right, process. So fatty acids released into circulation, and majority of fatty acids being uptaken by muscle. How much? Yeah. Like 70%, right? So fatty acids is picked up by muscle. And how does the muscle do with the fatty acids? Oxidize, right? Complete oxidize for energy, ATP. And also 1/3 of fatty acids, right? Picked up by liver. And what liver does to synthesize ketone bodies, right, and release the ketone bodies into circulation. And again, these two, brain and muscle, are the major tissues that utilize ketone bodies. And the difference between brain and muscle in terms of utilization of energy fuel is that the muscle utilize both fatty acids, but majority fatty acids, right, and also ketone bodies, but brain only be able to utilize ketone bodies for energy. And I just like, the small, very small amount of a ketone bodies can also be utilized by other tissue, but again, brain and muscle are the two major tissue, right, utilize ketone bodies. I can upload this slide. I don't think you guys have this slide, right? In your notes, okay? Okay, now let's talk about more details. So far, I just gave you kind of overview, right? At the tissue level and how fatty acids be mobilized during the fasting. Now we get the details. How fatty acids is oxidized for ATP production. Yeah, I think we basically talk about this already, right? And so we're going to focus on here the fatty acid oxidation. How fatty acids being oxidized in muscle and the liver, particularly, right? So in order to be oxidized, fatty acids need to be activated first. So if you still remember, we also talked about this reaction, right? The fatty acid oxidation to activation to fatty acyl-CoA by fatty acyl synthetase, right? This reaction, do you remember in which process, a pathway that we already mentioned this? Triglyceride synthesis, right? Triglyceride before, adding to the glycerol backbone, fatty acid also need to be activated to fatty acyl-CoA. So this reaction actually both basically is common, the same for both fatty acid oxidation and triglyceride synthesis, right? And this reaction requires ATP, so utilize 1 ATP for the process. And again, this process occurs in the cytosol, right? Fatty acids activation to fatty acyl-CoA occurs in the cytosol. This is just a numbering system, right? You already mentioned, but just want to remind you that the alpha, beta, and gamma, right? The carbon position, alpha is the carbon that next to the carboxyl group, right? Named as alpha carbon and then beta carbon. So the reason I wanted to mention this is that the next step we're going to talk about fatty acid oxidation, or it's called beta oxidation, right? So beta oxidation basically the breakdown the carbon chain between alpha and beta carbon right here. So each time when fatty acids oxidize, fatty acid oxidation also undergoing like cycling, right? Each cycle you remove the 2 carbons, from the fatty acyl-CoA molecules. So basically break down here between alpha and beta carbon and release a 2 carbon unit that is acetyl-CoA molecules, right? So here is the overview of beta oxidation. So let's take the palmitate fatty acids as the example. So again, you cleave the carbon between alpha and beta, and each time at each cycle you release the 2 carbon unit acetyl-CoA, right? And you have remain the acyl-CoA molecules with 2 carbon shorter, right? And this process also goes the cycling. So eventually you cleave and you break down the whole fatty acid molecules and release the 8 acetyl-CoA molecules, right, from the palmitate. So palmitate, again, if you remember, the 16 carbons, right? An important thing that you need to remember, the fatty acid oxidation or beta oxidation usually takes place in mitochondria, right? So mitochondria is very important. So that's why in the red blood cells, because it lacks mitochondria, right? So red blood cells are not able to do the beta oxidation. So that means red blood cell cannot utilize fatty acids for energy. Okay, now let's go back to the fatty acids oxidation. We mentioned fatty acids, first of all, need to be activated, right, to fatty acyl-CoA molecules in the cytosol, and beta oxidation occurs in mitochondria. So how fatty acyl-CoA molecules being transported into mitochondria? And mitochondria has a 2 membrane, right? So this just show you the mitochondria, the outer membrane and inner membrane. And this mitochondrial membranes are not permeable to the fatty acids molecule, fatty acyl-CoA molecules. So that means we need a transporter system to help fatty acyl-CoA from cytosol to the mitochondria for beta oxidation, right? So because a set of beta oxidation enzymes that located inside of mitochondria, right? So you have to get the fatty acyl-CoA molecule from cytosol into the mitochondria, then beta oxidation can occur, right? So there is kind of 4 enzymes that involved in this transport of fatty acyl molecules. 2 are located in the outer mitochondrial membrane, the other 2 in the inner mitochondrial membrane. But I just want you to remember 1, right? This is a key enzyme that catalyzes the transport of fatty acyl-CoA across the mitochondrial membrane, which is, I highlighted red, carnitine palmitoyl transferase 1, called a CPT1, right? Try to remember this enzyme that's located in the outer mitochondrial membrane. That is a key enzyme that controls transport of fatty acyl-CoA from cytosol into the mitochondria for beta oxidation, right? So I just describe maybe briefly how fatty acyl-CoA molecules is transported, right, into across the mitochondrial membrane. So first reaction is, you know, that fatty acids is activated to fatty acyl-CoA by fatty acyl-CoA synthetase, right? And first of all, this CoA being crossed through the outer mitochondrial membrane, right, and to the interspace, and carnitine is the molecule that can interact with the acyl-CoA molecules and to form acylcarnitine, right, in the interspace. And the acylcarnitine molecules then be transported across the inner mitochondrial membrane into the mitochondrial matrix, right, inside the mitochondria. And this is the enzyme that catalyzes, you know, the cross, right, the transport. And this transporter coupled with the carnitine molecules. So one acylcarnitine molecule is in, and the one carnitine molecule is out, right? And so kind of exchange, you know, the molecules and catalyzed by this enzyme, carnitine, acylcarnitine translocase, right? So once the acylcarnitine molecules arrive inside of mitochondria, then it is be converted back to acyl-CoA and release the carnitine. So carnitine can be recycled, right? And acylcarnitine eventually, you know, available for beta oxidation in the mitochondrial membrane. In the inside of mitochondria, right? You know, so I don't think you need to remember all these steps, but just you know that the key enzyme, right? The 4 enzymes involved, but key enzyme, try to remember the key enzyme CPT1 that control the transport of acyl-CoA molecules from cytosol to mitochondria, right? And oxidation. So this is just the overall pictures, right? And you connect all, you started from the fatty acid activation to acyl-CoA and the transported from cytosol to into mitochondria and controlled by CPT1, and then enter the beta oxidation process. So all these steps that involve, the oxidation of fatty acids. And what you need to know is that fatty acid beta oxidation also running cycle, right? And each cycle release the 1 2-carbon unit acetyl-CoA molecules. And second thing that you need to know is that during the beta oxidation, 1 FADH and 1 NADH reducing equilibrium molecules are produced by each cycle. And eventually the acetyl-CoA molecules, once it's released from fatty acid molecules, they enter the TC cycles for complete oxidation and ATP production, right? So I'm not going to go to each steps, what kind of enzyme that catalyze or something like that. You don't need to remember, but just a general, idea about how fatty acids is oxidized through beta oxidation, right? And all this sets of enzymes that are located in the mitochondria. So again, fatty acyl-CoA molecule has to be enter the mitochondria, right? And then be able to oxidize. So the final product of beta oxidation is, what is the final product of beta oxidation? Don't think about ATP, Say that, I'm sorry. Right, but the final product of the beta oxidation itself from the fatty acid molecules and break down each cycles, release acetyl-CoA. Yes, so acetyl-CoA is the final product of beta oxidation. And what does acetyl-CoA molecules go? Eventually, TC cycle, right? And for complete oxidation. But you mentioned the FAD and NADH is part of the product, right? Related to the ATP production. Final product is acetyl-CoA, but you also generate 1 FADH and 1 NADH each cycle, right? And this is again just going to the details, how this enzyme CPT1 control the transport of acyl-CoA into the mitochondria. And that's just the details of each steps, right? And the reactions. So now energy. So I think we mentioned this earlier. Why more energy is generated from fat than carbohydrate, right? Remember, only 4 kcal of 1 gram of carbohydrate can produce, but 9 kcal, right? 1 gram of fat can produce 9 kcal of energy. If you try to calculate the ATP production from the 1 molecules of fatty acids, then you probably get a better idea, right? Why fat can oxidation produce more ATP than carbohydrate. So in fat oxidation, for every loss of a 2 carbon, which is acetyl-CoA, right? How many FADH produced. Every loss, that means each cycle, one, right? One FAD and one NAD is produced each cycle. And each FAD H can produce how many ATPs, if you remember? 2 ATPs, right? And how about NADH? 3 ATPs, right? Very clear. No, not a 2 or 3, right? Because why? The NADH produced from beta oxidation generate 3 ATP. Yeah, because it's already in the mitochondria, right? So produce 3. Okay, now let's see. We take palmitate 6-carbon as the example, and how many ATPs can be produced from oxidation of one molecule of palmitate. If you're considering, this is a 6-carbon, right? And beta oxidation, how many acetyl-CoA units can be produced from beta oxidation of palmitate? How many? 8, right? Because it's 6 carbon. So each carbon you release 2 carbon acetyl-CoA. So 8 acetyl-CoA molecules can be produced from beta oxidation. And how many FAD and NAD? 8 or 7? I mean, no doubt, this is 8. Thinking about cycling, cycle, how many cycles then you need to do to complete oxidize the 7, right? Okay, so 7, that means you generate 7 FADH and 7 NADH, right? Okay, so, and we also know the final destination of acetyl-CoA is to TC cycle, right? And enter TC cycle, you generate additional ATPs, right? So thinking about, how many acetyl-CoA is generated from beta oxidation, and 8, right? And 8 acetyl-CoA molecules enter the TC cycles. So you put all this together and calculate the ATPs. So here's the equation. 2 ATPs, that means 7 multiplied by 2 ATPs, that means these 2 ATPs is from FADH, right? And plus 7 multiplied by 3 ATPs, these 3 ATPs from NADH, right? Does that make sense? Okay, so the 35 ATPs can be produced from beta oxidation of palmitate for complete oxidation, right? Does that make sense? And it's not N yet because all this acetyl-CoA will enter TC cycle, right? So you need to plus energies in generating from complete oxidation of 8 acetyl-CoA, right? Through the TC cycle. So 8 acetyl-CoA times 12 ATPs, right? One TC cycle, remember, right? Generate 12 ATPs, right? So 8 times 12, that's 96 ATPs. So you plus together 96 plus 35 will yield how many? okay, 131, right? ATPs. But if you still remember that actually how many ATPs are used? In which step? In the first step, activation, right? To acyl-CoA, and you use this 2 ATPs because the ATP be converted to AMP, not ADP, so this will consider 2 ATPs, right? And that's in that reaction. So 2 ATPs are used in the activation of fatty acids to fatty acyl-CoA reactions. So net yield will be 129 ATPs produced from oxidation of 1 palmitate molecules, right? So how many ATPs are produced from 1 molecule of glucose? You still remember? 36 to 38, right? So fatty acid oxidation can produce much more energy, right, than the carbohydrate glucose oxidation. And what about the carbon? The glucose only has a 6 carbon, right? And fatty acid, this palmitate is 18 carbon. So basically, take-home message is more carbon molecules and more carbons, then it contains more energies, right? All right. So for oxidation of unsaturated fatty acids, so I'm not going to talk about it, but just mention, because of the double bond, right? So you need to rearrange the double bond and to make at least the 2 carbon, beta carbon that available for beta oxidation. So it goes through the many additional steps, and also because of double bond present, so the unsaturated fatty acids basically cannot be completely, break down or oxidize. So you usually generate less energy compared to the saturated fatty acids, right? Okay. Now we finish the fatty acid oxidation, right? And we started from big pictures, of the mobilization, triglyceride release fatty acids during fasting condition, and then the fatty acids being utilized as an alternative fuels by primarily muscle, right? And liver for ketone body synthesis, and we also get to the details, right? How fatty acids being oxidized through beta oxidation, and also mention that fatty acids oxidation actually 2 steps, right? One is activation occurring in the cytosol, and then need to be, and the second one is the second step is the complete beta oxidation in the mitochondria. And we also mentioned that the transporter or fatty acyl molecules from cytosol to mitochondria requires a transporter system, right? You just need to remember CPT1 is the key enzyme that controls the transport activity. So this is very important process. Now let's talk about the ketone body synthesis or ketogenesis. So when do you think ketogenesis occurs? In which physiological conditions? Fasting, yes, the fasting, but just wanted to you note a little bit more the condition that prolonged fasting. If you're just fasting for a couple hours, and ketogenesis may not happen a lot, right? But only when we take very long time starvation, for example, longer than 2 days, then the ketogenesis will be very active, right? And this is a physiological condition, does that. But also, under the condition, that pathological condition, when fatty acids levels very high in the circulation, for example, diabetic condition, right? Type 2 diabetes patients, if you guys probably notice, when you well, maybe I'll talk about it later. So, type 2 diabetic patients usually have some problems with the fat tissue function. So fat tissue cannot store very well the fatty acids. So fatty acids release of triglyceride break down to fatty acids. This process called lipolysis, right, is increased. So they usually release a lot of fatty acids, be not able to store in the fat tissue, so causing the increased fatty acids level. And these fatty acids can be picked up by the liver and for ketogenesis, right? So again, try to remember the two conditions: the physiological condition and normal condition, that prolonged starvation longer than 2 days, and ketogenesis is very active, and the other condition is under pathologic condition, disease condition, right? Type 2 diabetes, when you have very high fatty acids levels, it can also promote the ketogenesis. So it's very common, right? The ketoacidosis, thank you, is very active, right, in the type 2 diabetic patients. So in which tissues does it occur? We talked a lot, right? Which tissues? Liver? Yeah, liver is a place that synthesizes ketone bodies, right? So, and fatty acid oxidation is this sort of the process, in the liver. Fatty acids oxidize to acetyl-CoA molecules, and some of the it will go to the TCA cycle, but it's very little, right? And majority of acetyl-CoA will actually go to the ketogenic pathway in the liver for ketogenesis, and utilized by these tissues, right? Brain, kidney, muscle. Okay, so I guess, just last thing, why we need to do the ketogenesis? Yeah, primarily because the brain cannot utilize fatty acids, right? So we need to make something smaller, so then brain can pick it up and use for energy. Okay, we have informal writing, right? Okay, let's just stop here.